Today we're going to talk about some advanced types of electronic filters. We're going to cover three types of filters in this presentation: band pass filters, band stop filters, and LC filters. You should already be familiar with RC and RL filters in order to understand the material in this presentation. If you haven't learned about those yet, you can click on the link at the top of the screen to see a presentation about them. We're going to start by talking about band pass filters. So what is a band pass filter? Well, it's a type of filter that allows a certain band of frequencies to pass through and blocks out or absorbs the other frequencies. A frequency response curve might look like this. The frequencies in the middle go through, and the frequencies above or below that band are blocked out. So what are band pass filters good for? Well, in the last presentation we talked about how they could be used to direct middle frequencies to mid-range speakers, or to listen to a particular radio station. Another good application for bandpass filters is in graphic equalizers. What happens with graphic equalizers is that each of the little sliders is assigned to one bandpass filter that allows a certain band of frequencies to go through. So in this case, you can see that on the leftmost slider, there's a number 20 above it. That corresponds to frequencies around the 20 hertz band. And then the next one is at 25, and then 32 and 40, and so on. So each one of these little sliders is assigned to a bandpass filter that allows only those frequencies to go through. And if you move the slider up, it allows more of those. It amplifies the frequencies in that band. If you move it down, it decreases the amount of those frequencies. So with this graphic equalizer, you have 31 bandpass filters for each channel, and you can amplify or diminish the frequencies from each of those bands. Now that we know what bandpass filters are and what they're good for, let's talk about how we can actually make them. We're going to start with some building blocks that we're already familiar with. So we know how to make a high-pass filter, and we know that it allows the high frequencies to pass through, these frequencies there. We also know how to make a low-pass filter, and we know that that allows the low frequencies to go through. It would be nice if we could combine these two types of filters and allow only the frequencies in the middle to go through. And it turns out that's pretty much what we do when we want to make a bandpass filter. We take the two circuits that we have for the high-pass filter and the low-pass filter, and we put them together. And by combining them in series like this, we create a bandpass filter. And when we do that, the frequency response looks like this. Pretty much what we would expect. Now let's talk about band stop filters. So what is a band stop filter? Well, it's a type of filter that allows high frequencies and low frequencies to go through, but it blocks just a particular band of frequencies. A frequency response for a band stop filter might look like this. One common application for band stop filters is in radio. In radio applications, band stop filters can be used to remove a powerful band of frequencies in order to prevent them from overwhelming weaker signals nearby. For instance, commercial FM transmissions are very strong. They are in the 88 MHz to 108 MHz band, and they can overwhelm nearby signals. So you may want to implement a band stop filter in order to block those powerful FM signals in order to hear FAA radio traffic in the nearby 118 to 137 MHz band. Now let's talk about how we can actually make a band stop filter. We already know how to make a low-pass filter like we saw before. It allows low frequencies to go through. And we know how to make a high-pass filter that allows high frequencies to go through. And we'd like to combine these somehow so that we make a band stop filter that allows low and high frequencies to go through, but blocks out frequencies in a middle band. Now, we saw before that if we put a low-pass filter and a high-pass filter together in series, it creates a band pass filter. That's not what we want. So instead of combining these two filters in series, we combine them in parallel, like this. This allows the low frequencies to go through the low pass filter and the high frequencies to go through the high pass filter, but the frequencies in the middle don't have anywhere to go, so they get blocked out. When we do that, the frequency response of the band pass or the band stop filter looks like this. Now let's talk about LC filters. So what is an LC filter? Well, L stands for inductor and C stands for capacitor. So an LC filter is a filter made with an inductor and a capacitor. We already know that we could make low-pass filters with either capacitors or inductors, like this or like this. And when we do that, the filters have a frequency response that looks something like this. If we look closely at the frequency response, we can see that the magnitude of this response decreases by a factor of 10 every time the frequency increases by 10 times. So what we can do to make an LC filter is that we can combine the capacitor and the inductor into just one filter, like this. When we do that, we get a frequency response that looks like this. If we look closely at this frequency response, we can see that the magnitude drops off much more quickly. It decreases 100 times each time that the frequency increases by a factor of 10. So the slope is 10 times greater than it was previously. However, there is this amplitude peak right at the cutoff frequency. This is called a resonant peak because the frequency or the filter actually resonates at that particular frequency. So that's slightly undesirable. The cutoff frequency and the resonant frequency can be calculated with this formula. And just like RC and RL filters, LC filters can be made into either high pass or low pass versions. Let's review what we learned about band pass, band stop, and LC filters. Band pass filters allow a certain band of frequencies to go through, but they block out or absorb other frequencies. They're good for audio applications like graphic equalizers or sending mid-range frequencies to mid-range speakers. And they can be made by putting a low-pass filter and a high-pass filter in series. Band stop filters reject a certain band of frequencies, while allowing lower and higher frequencies to pass through. They're good for blocking certain bands of radio frequencies in particular, and they can be made by putting a low-pass filter and a high-pass filter in parallel. Finally, LC filters combine an inductor and a capacitor in one filter. They're good because of their sharp attenuation that allows you to reject certain signals that are near other signals of interest. These are just a few of the advanced types of features. There are many other filters out there, many other designs for these types of filters as well. So these are just a few, but hopefully it gives you a taste for some of the things that you can do with electronic filters.